Hey, welcome back to Calculus. In section 5.2, we're going to continue the work that we started in 5.1, motivating this topic really with the area and the distance problem. If you've watched that video, then you'll recall that both of those problems, or approximations to their solutions rather, led us to considering certain kinds of sums. And those sums are called Riemann sums. So I want to give a definition of what a Riemann sum is here in this video lecture. We're going to define the definite integral. It's a limit of Riemann sums, okay? Those limits can be a little bit difficult to compute, but I want to be able to at least compute them for polynomials of degree less than or equal to 3. So I'm going to show you how to do a Riemann sum limit calculation for a polynomial that's at most cubic. In this video lecture, I'm only going to do one such example. It's quite a bit of computation, and it'll make the video long to do more than one, but I will make a separate video where I do at least one more, maybe two more. Then we'll talk about some applications of this definite integral. Some of them we already know, area and distance. They were motivating it in section 5.1. I want to kind of slightly expand that to something called net area and displacement, and then hint that there's actually a very large family of interesting applications of the definite integral in science and mathematics. And then we'll finish by looking at some properties that are similar to properties of limits and derivatives that just facilitate calculating these integrals. Okay, so let's start off by looking at the definition of a Riemann sum. It's a busy slide. I wrote most of this out, but I'll write some of it as we go later on in the lecture. But so what do we start with? We have to have a continuous function on a closed interval. Okay, so those are kind of the ingredients. You're looking at a picture of one on the right-hand side there. It's a continuous function on a closed interval. And then you have to choose some integer, whole number, I mean n. It's the number of rectangles or subintervals that you're going to use in your sum. So you pick it. It has to be at least one. And then we compute the width of the intervals. They're all equal width. And in particular, you take the total width, b minus a is the total width of the interval from a to b, and you just divide that by the number of rectangles that you are using, right? So that'll give you n equally wide rectangles, or intervals, if you like, on the x-axis. The endpoints of those intervals, I'm going to denote them by x sub I. And how do I find them? Well, starting at a, the leftmost endpoint, I just multiply I by that step size to get to the ith endpoint, yeah? So if I start at A and I add 0 delta x's, well, that gives me A. If I add 1 delta x, I'll get x1. If I add 2 delta x's, I'll get x2, and so on. If you add n of these delta x's, well, n of the delta x's is just b minus a, and if you add b minus a to a, you get b. All right, so those are your endpoints, formulas for them in terms of the counter, and that counter goes from 0 to n. And then we choose our sample points. You can see them in this picture. They're kind of chosen randomly. We'll usually choose them to be the right endpoints of these subintervals, but in general, you can pick these sample points, these xi stars, to be any number in. That's all I mean by this symbol. Xi star is between xi minus 1 and xi, and I call those the sample points. And then you plug those sample points into your function. In the picture you're looking at here, if I just picked on, say, xi star, I think of f of xi star as the height of a rectangle. Yeah, the height of that rectangle is f of xi star. It's written in the picture. What's delta x? Delta x is the width of the rectangle. So for this particular picture, if you multiply height times width, you get area. So this Riemann sum just represents the sum of these n rectangles areas. And like we saw in section 5.1, that gives us an approximation for the area under the curve. The approximation getting better and better as n gets bigger and bigger. The rectangles fit better and better. Okay, but in general, a Riemann sum is found by just partitioning your interval into these equally width subintervals, choosing a point in each subinterval and plugging it into your function, multiplying the output value by the width of the subinterval and adding them all up. Okay, and that's called a Riemann sum. Cool. The definition of the definite integral, continuing along. So here's the notation for it. I'm going to say something about this notation, but I'm making a definition. The definition of a definite integral, this is its notation. It's the quantity that I'm defining. It's just the limit as n goes to infinity of those Riemann sums. All right. So for each n, you choose these sample points, you plug them into your function, multiply them by delta x, add them up, and then you increase n without bound. And if that limit exists, then we'll call this number the definite integral of f over ab. All right, let's analyze that notation a little bit. It's kind of a busy notation scheme. So here I've got written in black this definite integral of f over ab, and let's just talk about some of the symbols in the notation. So first of all, this elongated kind of S-shaped thing is called an integral sign. It was first written down, if I'm not mistaken, by Leibniz, and it's because it's the limit of a sum. So it sort of looks like this S. It's called the integral sign. On the integral sign, we write the quote unquote limits of integration. That is the extreme endpoints of the interval. The one that we write on the bottom is called the lower limit of integration, and the one on the top is called the upper limit of integration. The function that we're, the process of computing a definite integral is called integrating the function. So the thing that we're integrating is called the integrand. Okay, and then this piece of the notation, you might recognize it from the linearization section where we were talking about differentials. It's not unrelated. It's not randomly written here, but for right now, at this point in our storyline, it's just playing the role of telling you what the name of the independent variable is, what the input variable is. So if you like, as n goes to infinity, our delta x, our subintervals become infinitely thin. So you can kind of think of this dx as an infinitesimally small change in x. So when you look at this integral sign, you can, if you're thinking about the picture in the previous slide, you can still think f of x is height, dx is like this infinitesimal width, so their product is an infinitesimal area. And we've somehow summed over infinitely many rectangles to get the exact area in that one context anyway. Okay, so that's just sort of the nomenclature of the definition. What are some applications of this thing, of this definite integral? As motivated in section 5.1, if your function is non-negative, that's what that says. It's kind of hard to read, sorry about that. If your function is greater than or equal to 0 on AB, then this definite integral just represents the area under the curve. That was one of our kind of defining or motivating examples of why we were even looking at Riemann sums. Or towards the end of section 5.1, if you had a positive velocity function, yeah, the definite integral, and notice here I'm using the input variable t. V depends on t, so I don't write dx, I write dt. But the integral from a to b of a positive velocity function would be the distance traveled. That was motivated in section 5.1 again, and you can look at the notation. It kind of reminds you that velocity, right, is a rate. It would be in something like meters per second, maybe. dt is a change in time. It's in seconds. Well, meters per second times seconds is meters. So the units kind of work out. Here's kind of a new one, the third one we didn't talk about in section 5.1, but I'm just going to throw it out there. If g of t is, say, some growth rate, you can assume it's greater than or equal to 0 if you want to, but g of t would be in units of like individuals per time unit, yeah? Maybe narwhals per year or something like that. And the change in t would be in years. Well, narwhals per year times years is narwhals. So the application of that integral would be the change in the population size. Okay, in section 5.4, we'll analyze this idea about how an integral gives a net change in detail. But right now, I'm just kind of trying to motivate you thinking like, well, you know, this number, this definite integral, it has some potential to answer lots of interesting science questions. The fourth example, I want to include a little picture. The author calls the integral, so if you relax the restriction that f be greater than or equal to 0 on the interval, then the author calls this integral the net area. So what is net area? Well, let me explain it to you. This picture on the right is kind of, I think, a nice thing to look at while we're talking about this. When you plug in your sample points, yeah, if you picked a sample point, I'm just going to choose one over here for you, for which f of x was less than or equal to 0. Where's the height of that rectangle? It looks like it's right there. So when you plug in that sample point, this xi star, well, f of it is less than 0. Right? So therefore, f of xi star times delta x is not the area of the rectangle, but rather it's the opposite of its area. So what the author is showing us down here is you're going to kind of count that area as a negative. So whenever you have regions of the curve that are below the x-axis, the area between the curve and the axis is sort of counted in a negative sense. For regions that are above the x-axis, the area is counted in the positive, usual sense. And so that's what the author means by this net area. It's sort of counting positive up here, negative down there. So the answer will be positive or negative, depending on whether there's more area above or below the curve. Okay, so you can always talk about the integral of a function over an interval being area, but if that function is not greater than or equal to 0, then that area isn't necessarily positive, and in particular, it's sort of telling you the difference between how much was above and how much was below. Okay, so there's another application. That limit definition is pretty intimidating, the limit of Riemann sums. Here you can see it again in the middle of this theorem 4. So we won't approve this in this class, but it is a fact that as long as your function is continuous, in fact, it's kind of an amazing fact that your function can be discontinuous if it only has a finite number of jump discontinuities. You can actually even make a stronger statement than that, but I won't get into it. But the function can actually have some discontinuities as long as they're not kind of infinite jump discontinuities. Then this integral will exist, that limit will exist. And when that limit exists, we say that the function is integrable. So lots of new vocabulary here, but integrable just means that that limit exists. And it doesn't depend on the sample points. These are all very deep mathematical theorems, that limit, when it exists, it doesn't matter on how you choose the xi stars. It's very, very sophisticated stuff, but we're just going to take it for granted. So since it doesn't depend on how we choose the sample points, we're always going to basically take them to be the right endpoints of the interval. All right. So we'll always compute this integral by taking limits of Riemann sums where we're going to use the right endpoints. So we'll take xi to be a plus I delta x, and we'll start I equal to 1, and we take it up to n. So those are always going to be our endpoints. Okay, I want to be able to compute limits like this for polynomials that have degree less than or equal to 3. So the next thing I want to do with you guys is compute one of these things. I've got it written out, so I'm just going to walk you through the computation for a degree 2 polynomial. I'll make a separate video maybe where I do a degree 1 or a degree 3, and then I'm going to ask you to practice it in the homework and in the activities. Okay, so what we're doing, let's just see it. We are going to compute the value of this definite integral, the definite integral from 0 to 4 of x squared plus 1 dx, by taking the limits of Riemann sums. Okay, so we're going to do this by definition. So let me start walking you through the computation. When you're doing one of these things, you choose n, and we're going to not choose a specific n, but we let n be a variable because we're going to eventually be letting n go to infinity. Yeah, so we're not going to choose a specific n, but I do start off by calculating my interval width, my delta x, and it's always calculated the same way. You take b minus a. Yeah, so our upper limit of integration is our b, our lower limit of integration is our a. You take b minus a and you divide it by n, the variable number of rectangles. So in our particular example, that's going to be 4 over n. And now I'm just using, I'm going to scroll a little bit here to go back. I'm using this definition for the endpoints. The ith right endpoint is always a plus I times delta x. All right, so that's what I'm computing down here. My ith right endpoint is a, that's 0, plus I times delta x. Delta x is 4 over n. And I've just algebraically simplified that. Okay, so that's 4i over n is my ith endpoint. I'm going to take I from 1 to n in the sum down here because I'm going to use right endpoints, but that's all of them. X sub 0 is equal to a itself. Okay, now we're applying the definition. The definite integral is the limit of the Riemann sums. So what I've got written right here is a Riemann sum. I'm using xi star equal to xi. I goes from 1 to n, right endpoints. But now what does that mean? This f of x is x squared plus 1. So what do I do with this xi, this 4i over n? Well, I plug it into the formula everywhere there's an x. So if f of x is x squared plus 1, let me write it out here. f of x is x squared plus 1. Xi is 4i over n, so f of xi then looks like 4i over n squared plus 1. And I have to multiply that by my delta x. And now I'm just going to do some algebra with you guys, kind of one line at a time. 4i over n squared is 16i squared over n squared. That's all I did in that line. And now I'm going to distribute the 4 over n. So 4 over n times 16i squared over n squared gives me 64i squared over n cubed. Multiply it by 1 and you get 4 over n. Okay, this is kind of similar to the calculation we did at the end of section 5.1. Yeah, this is why we did it. Now I'm using properties of sums. If I can rearrange these terms, I'll add up all these things first and then add up the second ones. So that's from Appendix E. 64 over n cubed and 4 over n don't depend on I, right? So they're constants, so they can be factored out of the sums by distributive laws. That's what I'm doing on this line. And now I'm using some formulas from the appendix, the sum of the squares and the sum of the constant 1. So I'm referring to those formulas on this line. Here's the sum of your squares. It's that cubic polynomial in n over 6. The sum of 1 from 1 to n is just n. And now to take that limit, it looks like my screen froze. That's unfortunate. No, it's back. Good. To take that limit, we don't have to multiply it all out. You can if you want to, but I'm just going to look at this thing and go, well, it's a cubic polynomial in n on top, and it's a cubic on bottom. So I'll just calculate the leading terms. The leading term at the top would be 64 times 1 times 1 times 2. That's 128 n cubed. The bottom is 6n cubed. I'm not writing the quadratic and the linear and the constant terms because they won't matter in the limit calculation. 4 over n times n is 4. Okay, the n cubes cancel, so that's 128 over 6. You have to add 4 to it, so we end up getting 76 over 3. So there you go. Congratulations. You've computed the definite integral of x squared plus 1 from 0 to 4 by taking the limit of Riemann sums. Quite a calculation. What does the calculation mean? It's a reasonable question. We just computed, this is a graph of x squared plus 1 from 0 to 4, and I've shaded the area below the curve and above the x-axis. And the exact area of that region is 76 over 3 square units. So whatever you're measuring x and y in, if they're in centimeters, this would be in square centimeters. If x and y are measured in feet, this would be in square feet. So I'll just write up here, square units of area. Cool. Okay, let's talk about some properties. I'll do another example like the one we just did, but in a separate video, so you can kind of stop and rest for a second. But let's talk about some properties. These are just things that are handy in computing the integrals. First of all, although it's not clear from the definition, there's no reason why the upper limit of integration has to be less than or equal to the lower limit or vice versa. So a and b can be any two numbers, really. And if you always want to put the smaller one on the lower limit of integration, you can do that. But if you switch the limit of integration, that's what this first property is. It's switching the limits of integration. Then you have to pay for it with a minus sign. The reason that's true is the delta x in these two calculations, if you calculated this thing, the delta x would be a minus b over n. Over here, it would be b minus a over n. And those are opposites of each other, right? So switching the limits of integration on an integral changes the sign of the integral, okay? A second little property here is that if a and b are equal, well, then b minus a is 0, delta x is 0, so this integral will be 0. That's kind of the area under the curve above a single point is 0. It has no width. Okay, so useful properties. Here are 4 more. These are very similar to the kinds of properties that we see, at least 2, 3, and 4, are very similar to the kinds of properties that we see for limits and derivatives. Yeah, what do they say? The integral of the sum is the sum of the integrals. You can pull constants through the integral. The integral of a difference is the difference of the integrals. Those are all very familiar sounding properties with respect to limits and derivatives. So they hold for integrals as well. I won't prove any of these things. You can come to an office hour if you'd like to ask about how to prove some of these things. Some of them are within our reach. The first statement is really just kind of a geometry fact that if you're integrating a constant function, if I kind of wanted to draw a little picture of that first statement, what's a constant function look like? A constant function, it only has one output value. That output value is c. So if you're thinking about the integral in terms of area, this integral, the integral from a to b of that constant dx, well, it's the area of that region. And that region, that region is a rectangle, right? So what's the area of a rectangle? Well, it's the height of the rectangle times the width of the rectangle. Okay, so that's all that formula says. I've got an example down here just to kind of quickly show you how you can use these properties. Suppose that we're given, and this is a true fact, that the integral from 0 to 1 of x squared is 1/3. You could prove that using limit definitions. Maybe you'll do it. So, but take that as a given, and then somebody wants us to find the integral from 0 to 1 of 6 plus 5x squared. So how do I do that with properties? Well, I basically use these properties to break it apart. Yeah. So the integral of 6 plus 5x squared, using a combination of properties 2 and 3, that's the integral of 6 dx plus 5 times the integral of x squared. Yeah, so I'm just breaking the integrals apart. The integral of 6 from 0 to 1 by property 1 is 6 times 1 minus 0. And the 5 times we were given the value of the integral from 0 to 1 of x squared is 1/3. So if you add it all up, you get 23/3. Okay. I want to do one more. My screen is a little laggy here. Hopefully I'm not going to have technical problems because I'd like to finish this video. But this is another useful property, that the integral can be split up. So if you're kind of looking at the formula, I would actually read it left to right. The integral from a to b, so you're thinking about as the area under the whole curve. Yeah, the area from a to b is the integral from a to b. This property is just saying that, well, it's the integral from a to c, so this sort of darker shaded region that I've just bounded above, it's the integral from a to c plus the integral from c to b. That's this part. Yeah, so it's just saying that the two areas together would add up to give the total area. And what's c? C can be any number between a and b. Okay, so this video, I know it's getting a little long. Let's just do one example that illustrates that last property and some others, and then we'll call it quits. So here you're looking at a graph of a function. It's called g of x. It consists of two straight lines and a semicircle. We're going to have to definitely use that information. Use it to evaluate each integral. Okay, so let's look at part A first. This part I haven't written out. So the integral in part A, the integral from 0 to 2 of g of x, since g of x is greater than or equal to 0 over that interval, is just the area under the curve. And the area under that curve is the area of a triangle. Yeah, because that's a straight line segment if we were given it. So what's the area of a triangle? Well, it's 1/2 its base times its height. So the integral from 0 to 2 of g of x dx is equal to, well, 1/2, the base of that triangle is 2, the height of that triangle is 4, so we would just get 4 square units of area. Okay. What about part B? Part B is asking us for the integral from 2 to 6. Well, here's the corresponding interval. So notice that that region, the area region, is going to be negative because it's below the x-axis. So to compute that integral, we could do it if we knew, well, the opposite of the area of that region. Well, that region, we were told, is a circle. So it's a semicircle. Its radius is 2, right? So what's the area of a circle of radius r? Well, it's pi r squared. You have to cut that in half for a semicircle. So the integral from 2 to 6 of g of x should be the opposite, because it's below the x-axis, of a circle of radius 2, but I want only the semicircle. All right, so you can calculate out that's what, minus 2 pi. Okay, and then finally, what about part C? Part C wants the integral across the whole interval from 0 all the way to 7. So now we're going to use that additive property. We're going to use that additive property that the integral from 0 to 7 of g of x, well, it would be the integral from 0 to 2, that's our 4, plus the integral from 2 to 6, that's our minus 2 pi, plus this last little bit, the integral from 6 to 7. I think my screen just froze and I don't think it's going to come back. Here, let me try to, sorry about this. My pen has been lagging and I'm not quite sure, but I don't want to start this video again. So let's see if that made it a little bit better. Yeah, I just have to do the integral from 6 to 7, right? Because we covered the integral from 0 to 2, that's our 4. We covered the integral from 2 to 6, that's our minus 2 pi. So we just have to add the integral from 6 to 7. And the integral from 6 to 7 is the area of another triangle. And that triangle's height and width are both 1. So that's going to be 1/2 1 times 1. And I'll let you calculate out that exact number. Okay, thanks for listening.